Right, thank you very much. So usually I give talks about operational problems and not so much fun like the previous speakers have done. This time I actually get to talk about fun stuff. We got a loaner AI200 system from DDN and we got to play with it for about 2 weeks, and I'm here to report about some of the results that we reached with it. So I'm Alf Wachsmann, you heard me on the panel already, and this is joint work with Alex Tuck from the Zuse Institute across town in Berlin. And as I said already on the panel, we don't really do deep learning, and so Alex was kind enough to help me run his example on the AI200, and you will see what that is in a second. So a few words about the MDC itself. Essentially, I could pull up the slides from Steve from earlier about the Crick Institute. We are about half the size, and everything else is the same except for two things. One is we don't do infectious diseases, and secondly, we don't have a queen in Germany. So Angela Merkel came out and pushed the button on our sequencers. But other than that, it's pretty much the same, and you can see on the bottom here all the techniques and technologies we're using. It's gene sequencing, microscopy, mass spectrometry, and so on. So that kind of unites all the different varieties of research areas in our institute. And that's all I'm going to say about the MDC. The Zuse Institute, where Alex is located, that's a real computer science institute. They are one of the tier 2 supercomputing centers in Germany. However, they don't have a DGX1. That is why Alex was very happy to work with me on this little project, because he got to play with the DGX1. So what is the problem? So Alex and his supervisor and some collaborators invented a new technique to look at MRI pictures and analyze the bone structure specifically for the knee. And they're using convolutional networks and the statistical shape models, SSM. And you will see in a second why we need the combination of all this. The technology in general is you put in these stacks of MRI images, run this through your deep learning pipeline, and then you get back the 3D shape of the knee. Goal of this is to detect early onset arthritis, so that then doctors can treat early enough that it doesn't get into severe problems. The network they're using is this UNet in a 2D version and in a 3D version. I have no idea what that means, what I just said, but that's what they did. Important is this next slide where you can see the effects of these. So on the left side, you can see if you only use the 2D convolutional network, and do we have a pointer here? Do you need to use the mouse? Here. So you can see if you're just using the 2D CNN, you get these weird artifacts here in the upper left corner. And then in another picture, you can see that you get these disconnected regions where the structure of the bone isn't really recognized. But that's the important part when you have arthritis. You get these kind of holes and indentations in your bones, so that's really important part. Then when you then add the statistical shape models, you get better, so you get rid of these artifacts, and in these indentations, you get a little. That's exactly what I was afraid of. And you can see it's getting better in these indentations, but it's still not where it needs to be clinically usable. And for that, the 3D CNN is then needed, where you can see that really the shape of the bone is really nicely modeled. So the result of this algorithm is that the Zuse Institute is now the top performer in the MICAI SKI 10 Grand Challenge, where they put out 150 of these volumetric MRI images and then ask people, hey, train whatever or use whatever algorithm you want and then tell us how the bone structure in the knee is. And these are 150 images, so not a big data set. And the goal now is, now that the algorithm has been proven that it works, they want to use it on the osteoarthritis initiative. That's an NIH-supported project where they have 50,000 of these MRI images or knee images. And it's obvious that you need to do something else compared to your 150 images. And that's kind of part of the reason why we collaborated on this. So Alex did then a few kind of rough estimates to see how long the whole thing actually takes if you would use his workstation. The algorithm scales really well with number of pictures, with number of images. So the inference stage, which is what really the 50,000 images have to go through, is on his workstation. So on an 1080 Ti NVIDIA GPU, it's about a minute. If you just take the GPU part of the whole calculation, and it's about 2 minutes if you take everything all together. Okay, just as a very baseline number here. And then on our DGX1 with the V100, again, only on one. So it's about 25% faster. Okay, no big surprise, but just to get an idea, an impression how long the 50,000 images would take. That's why we did that. And then just because we wanted to know that as well, we measured the training phase, and on that, the DGX1 is actually 2.5 times faster. Okay, so DGX1, that's what is inside one of these machines, and the previous tests and the baseline result compared to the AI200 is with the internal SSD RAID arrays. So inside these DGX1s are 4 SSDs, 1.92 terabyte each, and they are combined into a RAID 0 file system. And that gives about 7 terabyte usable space. So 7 terabyte is not too bad, but you can see 50,000 images won't fit on there. So that's the system we are using, just the internal SSD RAID arrays to do the comparison on my next slide. And then the loaner equipment from DDN was the InfiniBand switch and the AI200. In our case, it was or is a pre-production unit. So it took forever for the DDN engineers to figure out how to actually set this up. Many thanks to Jan Heichler, who put in quite a few work hours to set this up. And that is also the reason why we had only 2 weeks to play with it before coming here. I'm not saying these are preliminary results, it's only these are the first results we got. So we will do more testing, other testing to really kick the tires on the system. And again, this system here has 21, in fact, I think even only 20 SSDs in there. One is still sitting in a box, we never got around to install it. But it's meant to have like 24, 25 SSDs in it. So this is all pre-production and whatever, but you will see the results are already quite impressive. So these are the two kind of setups that we use, just the DGX1 with the data on the local SSDs, and then the same data, same software, same everything, but with the data on the AI200. And we used in our tests only one luster rail, or I should step back one step, James didn't mention that. DDN did a very good job in containerizing luster for the DGX1, because that's really how NVIDIA thinks everything should be done on the DGX1. So all the deep learning frameworks, everything comes in a Docker image, in a Docker container. And DDN worked with NVIDIA to package a luster client inside the Docker container. So you spin up this Docker container, and then you can run your benchmarks inside this container, which has then the luster file system over RDMA mounted from this AI200. So it's a really neat setup. I was very skeptical at the beginning, thinking, oh yeah, we spin up these luster clients and tear them down, spin up, take down, and so on. This will never work stably. But it turns out we didn't have a single problem. So these containers just start up, you can tear them down, no garbage left around, you can set up the next container, it just works. I was amazed to see that, so well done. Oh yes, and then per container in our setup, we can use a single luster rail, so there are 4 InfiniBand links going from the DGX1 to the AI200, and to really make use of all the 4 connections, so all the rails in Lustre. You're supposed to spin up then more Docker containers with these Lustre clients in it, and then run multiple of these containers in parallel. We were not quite prepared for that, to use that. We were more thinking running multiple of our learning or inference processes within one container. So we haven't done the multi-rail setup within one container yet. We are still working on this to get this set up. Due to lack of time, we didn't get around. But you will see the results are already such that we never really broke the AI200 into any kind of sweat. I mean, it handled everything just beautifully. And what we did was not even close to a stress test for the system, because we did the math. We used 500 images. Each image is 40 gigabytes roughly. And the inference and training with the numbers that I showed you, the amount of time it just takes from a computational side, the I/O side is not the bottleneck there. Okay, so this is number 1 of the results that we have. This is the training phase, so not the really interesting part, but still, because we are curious scientists, we wanted to know not just the inference part, but also the training part. You can see in red the wall clock time that it took on the DGX1 SSDs. And then on the lower right, the wall clock time it took on the AI200, so with the data on the AI200. And the graph here then is the ratio of the two. So look at the scaling. We are very close to 1. The AI200 is minimally slower than the internal rate in the training, but it's within the few percent, as you can see. Then if you look at the scaling, the purple line is ideal scaling, so from 1 to 8 GPUs in the DGX1. The green line is what we actually saw then in terms of scaling, going from 1 to all the way to 8 GPUs in parallel. And again, this is parallel over one rail within one container. It's not parallel over multiple containers. We don't know whether it makes a difference, but just to state what we did. So that's the learning phase with kind of half of our 500 images, so with 200 images. And then the inference state, that scales much better than the training phase. You can see the numbers are the same. So the red line is the wall clock time going from 1 GPU to all the way to 8 GPUs. And then the green line is the speed up then calculated. And here in the lower left is again the ratio of the 2 wall clock times. Here you can see that the AI200 for few GPUs is actually higher. So about 10% higher than the internal rate. But then when you get to all 8 GPUs, it drops dramatically. So we don't know whether this is an artifact of whatever else was going on. But I mean, overall, this looks really promising. And as I said, the deep learning algorithm we use is not at all I/O bound. And we haven't really use the full potential of the system. So for instance, you could, because this is potentially a shared file system, you could have ingest from one machine and do the learning on the other machine and so on. We didn't touch on that at all. So this is just the very first measurements, just comparing the DGX internal storage with the AI200. And so far this looks really great, and we're looking forward to more tests. And so that's what I wanted to tell you. Thank you.